Okay, we will continue our morning session, and the next speaker is Honglei Lang from the China Agricultural University, and the title of her talk is Multiplicative Multivector Fields and Forms Only Groupoids.
Okay, can you hear me and see my video?
Oh, sorry. You are in.
Can you see
Okay,
my
go ahead.
video? Okay. Okay, thanks very much. Yeah, okay. Thanks very much for the invitation. It's my great pleasure to give a talk in Poisson 2022. I'm very sorry I couldn't make it to Spain, so I just wish I can join you sometime. I can join you sometime soon in the near future. Okay. Today, my topic is multiplicative vector fields and forms on Lie points. And this is joint work with Zhuo Chen from Tsinghua University and Zhang Juliu from Peking University. Okay. These multiplicative structures, and as you have heard it many times in the previous talks, it's geometric structures that are compatible with the group-point multiplication. So related notions include Poisson group points and Poisson groups, of course, and multi-symplectic group points, Dirac group points, Glennon group points, Farfin group points, and quasi-Hamiltonian group points, etc. Many works about the universal lifting theorems or the Lie theory of these structures have been carried out, which means the correspondence between multiplicative structures on Lie group points and the infinitesimal structures on the Lie algebroids. Let me first give you some references if you would like to study this subject. The first paper is about multivector fields. And the second one is about forms. And the third one is about tensor fields. And the next one, this is a review paper if you like to study this multiplicativity. And the next two papers are two fundamental papers about Poisson groups and the symplectic group points. Okay, where our work was motivated most from the last two references. The first one is shifted Poisson structures on differentiable stack, and the second one is Poisson two groups. Okay. Here's my plan. The first two parts are parallel with each other. One is about vector fields and the other is about forms. They actually share many common features, and of course there are many differences. So my first goal is you can get some of the ideas from my talk. And I have actually reported the first part in Romania 2019 here. Okay. And in particular, we further study multiplicative forms on Poisson group points, because once there is a Poisson structure, then we actually have a bracket on our forms. Then some higher structures appear here. And yeah, actually here is the Lie algebras. Okay, these are the references. So let's start from the beginning. A K-vector field on a Lie group is multiplicative if its value at GR is a summation of pi r moving to GR and pi g moving to GR. In other words, it means the multiplication sends pi times pi to pi. Okay, immediately we get the pi at the identity is 0. Okay, one example, if tau is an element in wedge kg, then the difference of the right invariance, right translation, and the left translation is multiplicative. Okay, so a Poisson Lie group is a Lie group with such a multiplicative bivector field, and also it is Poisson. Okay, now let's have a look at the definition of a multiplicative k-vector fields on Lie group points. I will give three actually definitions, equivalent definitions. The first one is the original one. A k-vector field is multiplicative if the graph of group point multiplication is a co-isotropic sum manifold. Okay, in 3G. If unraveling this co-isotropic condition, we'll get the algebraic description. Let's see. So it has three conditions. The first one is like similar to the previous one in the group case. Here, GR is a composable pair. They can compose with each other. So the value of pi GR, and here, because we need to be very careful with the left translation and right translation. So we need to use bisections here. And another thing is the restriction of pi on the base manifold is not zero, so there is an extra term here. An equivalent statement about this condition one is the Scattern bracket of pi with the right invariant vector field is again right invariant. So here U is a section in A. A is the Lie algebroid. So in this way, actually, we can define this third pi, which is from gamma A to gamma wedge Ka. So if you are familiar with the Poisson group point, you can take in mind that K equals 2. Okay, so this actually will give a Lie bracket on A star. Okay. And the second condition means if C is a form on M, then T is the target map. So T star C is a form on the Lie group point. So the contraction is again right invariant. So based on this, we can define this third pi on a function. And it's defined in this way. This because this Scattern bracket is also right invariant. So this is well defined. Okay, the last condition is M. The base manifold is a co-isotropic sum manifold of G, which means the restriction of pi on M has no component in wedge gamma Ka. Okay, no component in this space. Okay, this is the algebraic description, and we have another one which is very useful actually. It's based on this fact. If G is a Lie group point, then we know that both the tangent bundle and the cotangent bundle are Lie group points. Okay, so we consider the direct sum of the cotangent bundle, our pi, which is a k-vector field. It sends k-1 forms to a vector field. So if pi is multiplicative, it means this map is a group point morphism. Is a group point morphism. So this definition 3 is actually very useful in our proof. Okay. Okay. So let's continue. So, and now we would like to understand better. This definition looks quite mysterious at first, right? So we would like to understand better of this definition. So in the group case, if pi is a multiplicative k-vector field, then we have a cocycle. We have a cocycle in the first cohomology of G with values in wedge K, the Lie algebra. So actually this C is just the pi G moving to the identity. So this means actually it's 1, 1. So we ask this question, can we do it in the Lie group point case? So for the Lie group point case, do we have such a one cocycle? And now we met two problems. The first one, we missed the first problem is there's not a normal adjoint representation about a Lie group point on its Lie algebroid, right? There are two solutions, I know. The first one is using representation up to homotopy. And the second one is to use the first jet group point. And here we adopt the second method because the first jet group point represents nicely on the algebroid, and here we add some YK. Okay. So another thing is, because for the Lie group case, we know the restriction of pi on E is 0. So what's that for Lie group point? If pi is multiplicative, so my question is, so what's the restriction of pi on M? Okay, here in their Poisson 2 group paper, they gave the answer. If pi is multiplicative k-vector field, although this pi restriction on M has many terms, but it is determined just by the leading term, this pi. All the other terms are obtained just by applying the anchor maps. Here, D rho is actually just the rho, the anchor map. So here, pi is the leading term. It's the component of 1 Tm because the k vector field. We take this leading term is 1 km wedge k minus 1a. So this pi plays an important role, and the b pi actually it can be written using the exponential function. Okay. Okay, we will also have this result in the form case. So I give it a notation of this summation as a b pi. Okay. So just combine these two results, we give our first definition. So here, so here, let me explain this jet group point. Maybe we're more familiar with the Lie algebroid case. If A is a Lie algebroid, then the first jet bundle is again a Lie algebroid, and this is an exact sequence of Lie algebroids. And on the group point level, we also have like an exact sequence of Lie group points. And here, this H is actually a Lie group bundle. Okay. So a characteristic pair of K0 type, we save the name of 0K type for forms. Okay, is a pair. We'll see the cocycle. Okay, and the pi is like in the space of the leading term, the pi in the previous slide. Okay, this satisfies the following conditions. The first one is pi is compatible with the anchor map rho. And the second one is the restriction of C on H here. The restriction of C on H is determined by pi in a complicated way. And actually, we can give it an explanation. The right-hand side is actually also a cocycle in this space. Okay. In short word, it's just the restriction of C on H is determined by pi in some way. Okay. So here is our first main theorem. There is a 1-1 correspondence between multiplicative k-vector field pi and characteristic pairs C pi. And they are related by the following nice formula. So here is pi g. For the Lie group case, we only have the first term. And here actually the second term, there's a b pi here. We know it's pi restriction on M. That's a b pi. Okay, so this is a 1-1 correspondence. Okay, one consequence of this theorem is we can use it to recover the universal lifting theorems for multiplicative vector fields. And actually, I will mention this for the forms. I will give the reference. Okay. So actually, the characteristic pair for the group case is just C0. Okay. And let's see an example. If tau is an element in wedge Ka, so the right translation minus the left translation is a multiplicative, and its characteristic pair, this one cocycle, is actually a coboundary. And our pi is just tau apply rho anchor. So it sends its wedge Ka, so we use anchor map to send one component to Tm. So finally, it's an element in one Tm tensor wedge K minus 1A. Okay, so now there's an observation that, or a fact that this space, the space of multiplicative K vector field is not Morita equivalent, is not a Morita invariant. So we consider the quotient space. Actually, it's just this exact case gives the following two quotient space. They can differ from each other by an exact, we call this case the exact multiplicative. Okay, and also we can define equivalence on such pi or leading term. Okay. As a consequence of our previous theorem, we got the following result. Just this quotient space of multiplicative vector fields is a pullback of these two maps. In another way, it means we have an isomorphism. So this space is isomorphic to the fiber product of these two space. Okay. So now let's have a look at the transitive case. The transitive case is much easier. We don't even need to use characteristic pairs, and we can have an explicit interpretation. Okay, here's the transitive case. Before giving the result, let me first introduce the space. For transitive groupoid G, we have a product space. Because G, we don't need to use the J groupoid here. This G represents nicely on kernel row. So this is the first comerge space, and then the second one is gamma wedge Ka. So we can define equivalency relation where the first component is R prime can differ from each other by a coboundary. And the next component, the second component is gamma prime can differ from gamma by an element in gamma in this kernel row. So our result is any multiplicative K vector field in the transitive case must be of this form. So it's not just the exact case, the right translation minus the translation. There is an extra term, this F. And this tells us two pairs in one equivalence class, they will give the same multiplicative K vector field. So consequently, we got the quotient space. The quotient space is isomorphic to the first comerge of G with values in wedge K kernel row. Okay. Any problem so far? Okay. Okay, before finishing this vector field, before finishing this part one, let us recall a result from Bonici and his collaborators. And this actually motivates our work in the following. Okay. So because, let me write this space again. On this space, we have a Scoton bracket. And this is well known. I learned this from Ping's work, from Ping Shi's work. These multiplicative vector fields are closed with respect to the Scoton bracket. So this is a graded Lie algebra. Okay. So this is a graded Lie algebra, and also this one by the multiplicativity. This one is like a graded Lie algebra model. So also you can have a bracket. This is defined by the del pi I just mentioned in the previous slide. Okay, so the result is there is a natural strict graded Lie2 algebra on this complex. Here this is strict, or you can say this is graded Lie algebra cosmodic. Graded Lie algebra cosmodic. this Li2 algebra is very fundamental in their work. Why? Because Li2 algebras, such Li2 algebras associated to Morita equivalent Lie group points are homotopy equivalent. So because of this, the homotopy equivalence class of this Li2 algebra is considered as the space of multivector fields on the corresponding differentiable stack. Okay, so you can have a look at their work. Okay. Okay, and they further define the Poisson structure on the differentiable stack as the Merge-Lang element of this Li2 algebra. Okay, such idea or this Li2 algebra is Morita invariant. Also, this idea is was also appeared in Berwick and Otis' work. Okay, especially when the dot is restricting on 1. When dot equals 1, this is actually a Lie algebra cost module, no graded. Okay, so let us recall the definition of Li2 algebra. This is just a Li2 algebra, not graded Li2 algebra. Okay, a Li2 algebra is the categorization of Lie algebra, and it's equivalent to two-term infinity algebra. Here I just use this two-term infinity algebras. It is a complex of vector spaces, and it has two brackets, which maps G0 to G0 and G0 G-1 to G-1. And also it has a three bracket, which maps wedge3 G0 to G-1, and this satisfying the following conditions. Okay, the first one is the compatibility of the differential D and the two bracket. And the second and third conditions means the Jacobi identity of the two brackets does not satisfy, but not too bad, is controlled by the three bracket, and we also call it homotopy term. Okay, the last condition is actually a cocycle condition. Because when this G0, if we pretend this G0 is a Lie algebra and G-1 is a Lie algebra module, and actually this three bracket exactly, this condition is exactly a spherical cycle, the condition of spherical cycles. And it has 10 terms of two cans. Okay. And also you can understand this condition 4 as the compatibility of the two bracket and the three bracket. Okay. When this three bracket is 0, we call it is a strict Li2 algebra. So in this case, we have 1, and then this one tells us since the three bracket vanishes, so this means G0 is a Lie algebra. And the G-1, this one tells us G-1 is a G0 module. So, and we don't have this one. This one holds naturally. So this is the definition of Lie algebra cost module or strict Li2 algebra. This is the case in the previous slide, but there we just generalize this G0 G-1 as graded Lie algebra. Okay. So because also for this reason, we also define this. We always denote this two bracket of G0 G-1 to G-1 by this action notation. Okay, this is the definition of Li2 algebra. So what's a homomorphism between two Li2 algebras? Just look at this diagram. There are two Li2 algebras. So homomorphism. Then we first have F0, F1. They compose a train map. And then we also have F2. Here I use this dotted arrow to say that it's from wedge 2 G0 to G-1 prime. And this F0, F1 preserve the two bracket and the three bracket just up to homotopy. Up to homotopy means up to this F2. It does not preserve, it preserve up to homotopy. Okay, So what I'm going to do, I actually finish half of my talk, and actually what I want to do in the last half part is like that. Now let's record this little algebra here, this strict case here. Associated with our multiplicative vector fields on the Lie group point, we have like this strict little algebra, graded little algebra. And now we're going to talk about these forms on a Lie group point. So we hope to also get, actually there's a complex here. And our goal is to find a little algebra on the forms and a little algebra homomorphism between them. And this is our following goal. Okay. Any problems so far? Okay. Okay, no problem. Let me continue. So let's look at the definition of multiplicative forms. And this definition looks simpler, right? Okay, a K form on a Lie group point is multiplicative if just this one condition, where this M, PR1, PR2 are all from G2. G2 is the fibered product of G to G. The PR1, PR2 are the multiplication and the two projections to the two components. Okay, so together the three terms are all in this all K forms on this G2. Okay, so this is an equation on K forms on G2. So we also have two equivalent descriptions. The first one is a graph, like the geometric description. The graph of multiplication is an isotropic submanifold. Instead of co-isotropic, here is isotropic. Okay, and with respect to the forms. Okay, the second one is like the third definition for vector fields, and it's C#, which maps K-1 vector fields to of one form. This is a group point morphism. And so now so from the definitions, they look similar to the vector fields case. Okay, here's the first big difference. Because in the Lie group case, we know there are any degree multiplicative vector fields. But here, for Lie group, when K is greater than or equal to 2, all the multiplicative K forms are 0. So why? Because like theta acting on two vector fields, and then we write it as like a multiplication. And here this step we use our multiplicativity property, and we'll get it 0. So okay, this is the first example. So in the Lie group case, we only have non-trivial multiplicative one form. Okay. So another example is like if we have a form, let me write it here. If we have a form, so the S is the source map, T is the target map. The difference of this one, this is an example. Okay, this is just like our section in the vector fields, the left translation minus the right translation. Okay. Let's see more examples. So when we see a vector space as a abelian Lie group, so the K vector field, multiplicative K vector field are actually linear maps from B to Y to KB. Okay, just linear maps. So it's like linear. Okay. So the multiplicative one form, we only have non-trivial multiplicative one form. It's just V star. Okay. The next example is if we treat a vector bundle as a little point, where the both source and target maps are the projection, and the group point multiplication is a fiber-wise addition. So in this case, multiplicative vector fields and forms are indeed linear vector fields and forms on vector bundles. And actually, there are many works on this linear vector fields and forms. Okay. So also, I learned this from their paper. In this way, this is a linear case. Locally, it takes this form. Let's have a look. Here, pi is a k vector field on E. So locally, it takes the form here. Look at here. This P is the fiber coordinate. Q is the coordinates on the base. So linear means this linear function with respect to the fiber coordinate. So all the vector fields are partial P. And there's second term, there's no function about the a constant about the fiber coordinate. And here we can have k minus 1 partial P and 1 partial Q. Also, we can have the K form, the local form of a K form. And the one example I would like to mention is when, in particular, this E is the cotangent bundle of a manifold. And then actually, because we have a canonical two form, or dq wedge dp. And actually, this omega just maps the multiplicative K vector field to multiplicative K forms. And actually, it's an isomorphism of the two spaces. Okay, because it maps partial P to dq. Okay. Okay, now let's move along what we did for vector fields. If this theta is a multiplicative K form, we can still ask the question, what's its restriction on the base manifold? So the answer is as before. Although it has many terms, but it is determined by the leading term, theta. All the other terms are obtained by applying the rho star. Rho is anchor map. Okay. So here theta is an element in 1 A star K minus 1 T star M. Okay. And here, this is our characteristic pair of 0K type. It's a cocycle, where E is a cocycle in the first comodule of just 1G with values in wedge K T star M. Remember, in the vector field case, is just G wedge K A. We actually here we just exchange the positions of A and T star M. Okay. So this theta is element in A star K minus 1 T star M, and this satisfies the following condition. The first one is this theta leading term is rho compatible, and the second one is again the restriction of the E, the cocycle. The restriction of E on H is determined by theta, is defined by theta in a complicated way. And there's an extra one. Look at this one, which means E composed with rho star and send 1 T star M to A star. Look at here. Then it's a coboundary. It's a coboundary. It's just the D theta. And this one is very restrictive. Why? Because when rho is surjective in the transitive case, when rho is surjective, then our rho star is injective. This means this E is determining this E just a coboundary. So which means in the transitive case, it is very easy. Actually, it's just the coboundary case. Okay. So this is theorem. There is a 1-1 correspondence between multiplicative K forms and the characteristic pairs, and there's a formula here. And actually, this is not new. This result is a reformulation of proposition 4.1 in this paper, and where they actually use this idea to recover the universal lifting theorems for multiplicative forms and the correspondence with infinitesimal IM forms on the Lie algebras. And they write it by applying on elements. The difference of our formula with theirs is they write this formula by applying on elements. So on the right-hand side, it's a summation. There's a lot of terms. And because we did that on vector fields, we know this is just explicit. Okay. And of course, in this paper, actually, there's a bigger framework. They consider this multiplicative forms Lie group point with values in a module, actually in a Lie group point module, in a Lie group point module. So 2 examples. In the group case, the characteristic pair is there theta. There is no cocycle, just the theta, where theta is the G invariant elements in G star. And okay. And the second example is for this one. Our exact case, S star gamma minus T star gamma is characteristic is the co-boundary case. Okay. Okay, next is the transitive case. As I said, in this case, because of the third condition, if k is greater than or equal to 2, all the multiplicative k forms are the exact case. Okay, remember for the vector field case, there's an F here, there's a cocycle. Okay, this is one difference. Okay, and for one forms are special. Okay, I won't go into a detail. Okay. So now, actually, because on the forms we only have the Durham differential. On forms we only have the Durham differential. This it's easy to see the Durham differential preserves the multiplicativity. So as I said, I would like to find a higher structure or Lie algebra on this space. So that's why we consider these multiplicative forms on Poisson group points. Okay, let's go to our part 3. A Poisson group point is a group point with a Poisson structure which is also multiplicative. Okay, so with the Poisson structure on the one forms we have this P bracket. So extending this bracket to all forms by the Leibniz rule, we get the Kaozu bracket. It takes this formula. It's Kaozu bracket here. LP is the derivative P. Instead of preserving the degree, it lowers the degree by 1. Because the contraction of PP, the Poisson structure, lower degree by 2, and D increases by 1. So totally it lowers degree by 1. So here's my question. Multiplicative one forms closed with respect to the P bracket? Okay. The second question. All multiplicative forms closed with respect to the Kaozu bracket? And the first one is easy to answer by doing the Gardner calculus on multiplicative, Gardner calculus on multiplicative and multiplicative vector fields and forms. Actually, we will see the Lie derivative, the contraction, the Durham differential, all preserve the multiplicativity. But the second, this is okay. But the second one is not obvious. Why? Because even from the Lie group example, we know the wedge product on forms does not preserve the multiplicativity, which means the wedge product of 2 multiplicative forms are not is not multiplicative. So it's not obvious from this one. But by writing this one, by writing this Kaozu formula in a formula looks like this one, we solve this problem. So this is also yes. So here the off circle is not closed and the wedge product. Okay. This is let's make a summary of what I just said. For a Poisson group point with respect to the Kaozu bracket, we have that the first one is the multiplicative forms compose a graded Lie sub-algebra. Okay, the second one is this exact case. This exact case is an ideal. Okay, And the third statement is our P sharp. Maybe let me write it white dot P sharp, which sends multiplicative forms, K forms to multiplicative K vector field. This is a well-defined map, and it is a greatly algebra homomorphism. So actually, for our goal, the diagram, we finished the bottom horizontal line. Okay. And here, this is our Li2 algebra. Because because the exact case, we have a complex here. So we have a complex here with the with the P bracket on forms, and by the multiplicativity, this is a well-defined map. So this theta is here, gamma is here. We can define action. So here I use S star, or you can use the T star. S star is injective, so it's well-defined. Also, the well-defined of this formula of this action is based on the multiplicativity. Okay. So the result is this is a strict graded Li2 algebra, and this Li2 algebra, we have a graded Li2 algebra homomorphism. This is strict. Both graded Li2 algebras are strict, and the homomorphism is strict. The Poisson structure is the Poisson structure builds the bridge between them. So now, up to now, it's natural to ask the following questions. So, what about the case of quasi-Poisson groupoids? That's the first question. The second one is, can we get a weak Li2 algebra or Li2 algebra that is not strict? I think this is something we can expect. This is something we can expect. Okay. What about quasi-Poisson groupoids? And can we get weak Li2 algebras? Okay. Now it's part 4. A quasi-Poisson groupoid is a Lie groupoid P with, again, multiplicative bivector field P. It's not Poisson, but its PP bracket, its Scoton bracket is an exact one. It's here our phi is wedge 3A, so it's the exact case. And the second condition is the Scoton bracket of P with phi, the right invariant vector field on G is 0. Okay, so in this case, now we need to know now the bracket, the P bracket, does not satisfy the Jacobi identity, right? But what's the left? Okay, these are two important formulas I learned from Eva Kosman-Schwarzbach's paper. Okay, this important formulas give the answer actually. The Jacobi, here's theta are one forms on G, and the Jacobi identity is not 0, but it's related to PP in this way. Okay, it has four terms on the right hand side, and the second one is P sharp does not preserve the bracket, and it's related to PP in this way. So in the following, actually, we're going to use the right-hand side to define the 3 bracket. And when we write this PP as right invariant minus right translation of phi minus left translation of phi, and then actually we can separate the right-hand side in 2 parts. One is about the right invariant right translation, one is about the left translation, and take half a part defines the 3 bracket. And I'll speak the first. And this one actually tells us the Jacobi identity of this 2 bracket does not satisfy, does not hold, but it's up to this 3 bracket. And this one, the second condition, guarantees the compatibility of the 2 bracket and the 3 bracket in the definition of Li2 algebra, because it's P. Poisson actually gives the 2 bracket, and this phi actually gives the 3 bracket. And so this is, but not when I say it's very natural. Okay, let's look at the formula. So when we are given a Cauchy Poisson groupoid, then the triple is a weak L2 algebra. Weak means it's not strict. Where this J and the two bracket, the action are defined in the Poisson case, and we have extra three bracket in this way. And as I said, this one, because this S star is well defined, this S star is injective. Okay. And this is what this term is actually just half part of the right hand side of this formula. Okay. It is half part. I take the left translation, half part of the right hand side. Okay. And now I just give a one-line proof of this, because the compatibility of two bracket and three bracket has 10 terms. So I know for sure it's guaranteed by this relation of P and phi. But in what way? Here's the formula. And this is the 10 terms. The left-hand side is the 10 terms. We would like to show it is 0. And actually it's related to P phi in this way. It takes us quite a long time to figure out this formula. At first, we made the guess that it equals to this term. It's D something. And no, it's not. There's many extra terms, and at last we found out that it's just there's many terms here. So when P phi is 0, so the right hand side vanishes. So we get the result. And also, I would like to say, and here okay. Okay, I'll just skip this. Okay, this is the result. And now, recall this is just about one form, and we want to consider the K forms or all the forms. So because in the linear algebra, we know if G is a linear algebra, then Wedge dot G is a graded linear algebra. This is by using Leibniz rule. The definition is just by using the Leibniz rule. But in L2 algebra, can we say if G minus 1 to G0 is a L2 algebra, can we just wedge them? And using the Leibniz rule to get a L2 algebra, to get a graded L2 algebra? No, it's not right, because we have many extra terms, mixed terms, like some G0, some G minus 1. So because of this, we need to define the bracket directly. We can't just use the Leibniz rule. This is the point I want to emphasize. So we need to define the three bracket of them directly, not by using the formula on one form and by extending on the Leibniz rule. That doesn't work. And here we need to define it directly. Okay. Here the complex is as previous. The two bracket, the P bracket is as previous, like the Skelton bracket, and the action defined similarly. And the three bracket here I need to explain the notation. Here there are 5. Here this theta 1 is a P form. This is a P form. Let me just say a multiplicative P form. And our 5, the left translation is like a 3. Is the 3 vector field. Here we have 3 layers of contraction. And for one contraction, actually the first contraction, the result is it's just a contraction of one vector field with a form. So then 2 vector fields and the P-1 forms are left. So finally, this IP sharp theta is a tensor. It's a 2P-1 tensor. Okay, so we take another contraction, then the vector field, the degree of the vector field decreases until to 0. And finally, we will get, after 3 layers of contraction, we'll get a 4. Okay, but we need to prove it is well defined because it's again like something in this space. Okay. And this is the final result. This is our final result. Okay, just on the form, on all the forms, we have a graded Lie-2 algebra, which is weak. And on the left-hand side, because of the Skelton bracket, this is strict. This is strict. And this is weak. And we have a weak Lie-2 algebra. We have a weak Lie-2 algebra. The bridge is our P and also our phi. Our phi will define the homotopy term. Okay. And this is the contraction in the definition. Here sorry. Okay, this is the contraction. Because in the second layer, we need to contract a tensor field with a form. So here it's just the contraction of one vector field with the form and leave all the other vector fields and forms. Okay, and finally, it's again a lower. It's a tensor field. And to prove our theorem, actually, we need to use this lemma. The contraction means the contraction. Here, actually, we need to use this multiplicative tensor fields. Okay, I already gave the reference. So here, the result is this contraction is again multiplicative. So all the things are multiplicative. Okay. So this is the corollary in the Lie group case. For the quasi-Poisson Lie group, and we know the P bracket on this one on all the one forms is there's no Jacobi identity, so it's not a Lie algebra. But restriction on multiplicative one form, we get a Lie algebra. This is a Lie algebra. Okay, so because in this case, because it's a Lie group case, we only have a multiplicative one form. So this is a Lie algebra seen as a Lie-2 algebra strict, and on the right-hand side, on the right-hand side, this is a strict Lie-2 algebra, and so both are strict. And there's a weak morphism between them. There's the two. This is the weak Lie-2 algebra homomorphism between two strict Lie-2 algebras, and this phi plays the role of the homotopy term in the homomorphism. And in our paper, we also considered in detail all the more examples like action points, and we would like to ask that what do they look like? What do multiplicative vector fields and forms look like on action legal points? Okay, and actually we can recover, our diagram can recover some of the Lie-2 algebra examples in literature. For example, this one. Let me write the diagram. In some cases, we will recover this. T is the Lie-2 algebra. And this is just a coadjoint. And this is a weak. We will recover some of the Lie-2 algebra and Lie-2 algebra homomorphisms in the literature. Okay, I'll stop here. Thanks for your attention.
Okay, thank you very much for your lecture. So there are some questions for Honglei. Sorry. Oh.
Hello.
Hello, can I stop? Okay, can I stop sharing so I can see?
Hello, this is Marco. So we had a question. So you said what happens for multiplicative structures on quasi-Poisson groupoids. Is there anything you can say about quasi-symplectic groupoids?
Quasi-symplectic groupoids. No, I haven't thought about that, but I think there must be some results, right? Yeah, it's a good question. I never thought about that.
Okay, thank you a lot.
Quasi-symplectic.
Wait,
Yes.
Honglei, I mean, those quasis,
Yeah.
Poisson groupoid, they are not containing quasi-symplectic as example. The quasi-symplectic is not a special quasi-Poisson.
The relation of quasi-Poisson and quasi-symplectic. I think quasi-symplectic is a special case for quasi-Poisson, right?
That would be nice.
Yes, yes.
And also then this Poisson wouldn't be just this one-shifted Poisson, you know, these Toan people, they have developed.
What Poisson?
One-shifted Poisson structure on one stack.
Okay.
Yeah.
Yes. That's why we consider.
Probably one can read some of their thing and try to connect. That
Yes. There one shift Poisson on differentiable stack is
right.
exactly actually quasi-Poisson on the groupoids.
Oh, then Then probably quasi-Poisson contain quasi-symplectic, right? Oh, that's very good. That's very good. So therefore, I guess you in this weekly 2 algebra you obtain, they are actually vector fields on the quasi or not Poisson groupoid, right? So they are actually the vector field on the one-shifted stack, one-shifted Poisson stack, right? So I would expect something like Morita equivalence preserving property. Do you have that? Like if one Poisson groupoid is Morita equivalent to the other quasi-Poisson groupoid, then the weakly 2 algebra you got will be, you know, weakly equivalent to the other. Do you have this?
Yeah, that's the next future work because
that would be very good.
The right side. This is invariant.
This is already invariant. Okay.
Yeah, this is
good
in
start.
their work. This is in the work, but the form, I don't know.
Okay, great. Then more future. Thank you very much. Nice talk.
Yeah, thank you.
Well, that's Anton. Thank you for a nice talk. Could you go to your last slide with corollary on quasi-Poisson groups?
Okay, this one. Okay.
Yeah, so I'm always wondering, so here you're using this phi, this Cartan 3 form, but what if you have some higher cocycle, whatever, a nice element in wedge 5 or some other odd element? Kind of would you have an analog of this theorem, some kind of higher version? I don't know whether this would require whether this would require a deeper, whatever, maybe not a 2 Lie algebra, 3 Lie algebra, but so can you incorporate higher elements? Thank you.
Okay, thank you for the question. Yeah, by my knowledge, I only know about this quasi-Poisson, and I only see this 3 like elements in Y3G, and I don't know, like I don't have the basic knowledge, so I will look into the reference and think about that. Thank you for the question. Yeah, you mean there are some elements in Y4G? Yeah, I will think about that. Thank you.
Sorry, I have a naive question. I mean, in the beginning, you define this B pi. It's the 1 minus exponential and quotient x. I think this is also the generating function from the Bernoulli numbers. So I just don't know why this formula appears there. I mean the Bernoulli numbers and for this definition of B pi. Yeah. Yes.
Yes. Sorry, I don't know. I don't have the answer for this. I will ask Zhou about this. And here we obtain this formula just by it's this actually this proposition or this proposition is easy. It's quite easy to prove just by this formula. It's determined just by this condition. This M is co-isotropic some manifold. This formula is obtained by this condition.
Okay, but why it is called B pi? The B, I don't. I mean, it feels like some Bernoulli number. So B.
Oh, maybe I learned this from their paper. So maybe
okay. Thank you.
No,
I will refer their paper. Thank you.
Okay, thank you.
Oh, yes, another one.
Only just a small comment. I don't know whether it's related. Figure out yourself. Don't answer wrong. That's one comment. The other thing is that, like this Bernoulli number, I have seen Getzler's formula for derived bracket. I don't know whether it's related, but could be a thing to check. Finished.
Okay.
Okay, so if there are no more questions, so thanks again to the speaker. Thank you very much.
Okay, thank you. Bye-bye.
And we have 5 minutes to start the new